In Chapter 5, we're going to introduce analyze systems in the frequency domain. So before we introduce the frequency analysis of the systems, we're going to first try to answer the question, why do we have to analyze signals in the frequency domain? So here is one signal with noise. We have one system that can be used to process the signal with noise. Or you may use another system. This is the third system. Apparently, you can hear some difference after the process. The three systems all give slightly different signals. So why the signals are all different? And here we can see that the three systems have different impulse response. But how could you interpret the resulting signals from these three different systems? It's kind of hard to explain the behavior of the systems in the time domain. So we can treat the system as a problem of signal transmission. So when you have an input signal, you transmit it through that system, you're going to get the output. In the time domain, we understand that the interaction between the input and the system actually can be described using convolution. So if we have a rectangle signal as the input, and it has happened that the system can be described by a rectangle signal as the impulse response, then the output can be predicted because we know the convolution of the two rectangle signal is a trapezoid signal. But what if these signals are not very regular? What if the system has an impulse response could not be described by a regular signal? So we're going to introduce in this chapter a new way. We're going to convert all the analysis from time domain to the frequency domain. You're going to see that in the frequency domain, the signal transmission can be interpreted using a more clear way. So we're going to start from analysis of continuous time LTI system. So here is what we learned in the time domain. The output of the system can be represented by the convolution of the input and the system's impulse response. Now, if we select the imaginary exponential signal e to j omega t as the input, let's see what's going to happen. Here is the definition for the convolution. And let's rewrite it because this part has nothing related to tau. So it can be moved outside the integral. And pay attention to the terms left inside the integral. It is actually the Fourier transform for h of t. So if we define capital H of j omega is the spectrum for h of t, then this is the final results for the zero state response. And we define capital H of j omega, the frequency response of the system. It is the Fourier transform for the system's impulse response. So it's very interesting that for an imaginary exponential signal e to j omega t, the output is itself times the signal's frequency response. So here is the explanation of the behavior of the system in the frequency domain. So for a stable continuous time LTI system, if the input is an imaginary exponential signal, then the output is the same imaginary exponential signal with the same frequency, while the signal is modified by the system's frequency response. It's quite straightforward. And the frequency response reflects the transmission properties in terms of the frequency components. Again, because the frequency response is the Fourier transform for system's impulse response, so in general it is a complex function. So it has amplitude and phase terms. The amplitude term is here named as amplitude response, and the system's phase response is defined as the phase part. So in case h of t is real, then based on the symmetry, conjugate symmetry, we understand the amplitude response must be an even function, while the phase response must be odd. And here is the relationship between the input system's impulse response and the output, or the zero-state response. While in the frequency domain, we know the correspondence, convolution in time domain, multiplication in the frequency domain. So we can, using another way to define the system's frequency response by this ratio. Next, we try to use Fourier method to describe a continuous time LTI system. So in the time domain, we often use differential equation to describe any continuous time LTI system. What if we take Fourier transform on both sides of the differential equation? It will become this equation using the differentiation properties in the time domain. By rearranging this equation, we can get the definition for the frequency response. And that value actually is related to the coefficients in the differential equation. Here's one example. The differential equation helps us describe a continuous time LTI system in the time domain. What if we want you to describe the same system but in the frequency domain, or in other words, what is the system's frequency response? So the idea is quite straightforward. We take Fourier transform on both sides of the differential equation. And here is the resulting equation. And by rearranging the terms in here, we can get the system's frequency response. The relationship between system's frequency response and the system's impulse response is clear. We already defined that they are actually a Fourier transform pair. But here we use another way to show the same conclusion. Because it is defined, the frequency response actually is equal to the ratio of the spectrum of the zero-state response and the system's input signal. And we can select the input signal equal to delta function. So the output will be the impulse response. And we know that this signal spectrum is equal to DC components 1. So we get the conclusion one more time. So they are all equivalent. There's one more example how we can use definition help us determine or describe the system in the frequency domain. Here is the system. We give the impulse response. So this is a description in the time domain. How can we describe the system, the same system in the frequency domain? We can simply do the Fourier transform to get the system's frequency response. So that is pretty straightforward. This is the system's frequency response. So we try to do a summation. The frequency response may be derived from the system's impulse response because they are a pair of Fourier transform. Second, the frequency response may also be derived from the differential equation. So here is the description in the frequency domain. And we know that this frequency response is determined solely by the coefficients in the differential equation. Although frequency response h of j omega is defined by this ratio, but we can see that the actual value has nothing related to the selection of the input or the system's zero-state response. Now let's try to study if the input signal is a sine signal, what will be the LTI system's zero-state response? So the sine signal can be represented by two imaginary exponential signals based on the Euler relation. And by the understanding, if this is the input, then the zero-state response will be the same imaginary exponential signal modified by the system's frequency response. And we know that if the system's impulse response is a real function, then the frequency response has conjugate symmetry. So the amplitude is even and the phase is odd. So we can combine them into this expression. Now it is clear that the zero-state response of the system is equal to the same sinusoidal signal, but the amplitude is modified by the amplitude response, and the phase is modified by the system's phase response. So by looking at the relationship between the input and the system's zero-state response, we understand that the response for a continuous LTI system to a sine signal with the frequency of omega sub none is another sine signal with the same frequency, but the amplitude is modified by the system's amplitude response, and the phase is also modified by the system's phase response. To summarize, this is the definition for the system's frequency response. And the concept for the system's frequency response can be represented by this diagram. The input, if the input of the system is an imaginary exponential signal, then the output or the system's zero-state response is the same imaginary exponential signal, but modified by the system's frequency response. And the frequency response reflects the transmission property in terms of the frequency components. And the frequency response includes two parts. One is the amplitude response, and the other one is the phase response. Thank you.